Hi, this is Melvin Mokhtari. In this presentation I'm going to talk about stretchable thermoplastic elastomer optical fibers for sensing of extreme deformations. This is a paper initially published on volume 29 issue 5 of the Advanced Functional Materials Journal in February 1st, 2019. The reason I picked this paper was that it was published in a really well-known journal in this field and also have received 159 citations, which is a good number for such paper in this level. They also applied their proposed approach in some applications much closer to the things we learned in the course. So that was the reasons I picked this paper for my presentation. So let's start with an overview of paper. Developing materials that combine optical and mechanical properties is a significant challenge in material science, particularly with soft materials for optical use. Stretchable optical fibers can withstand strains of up to 300% while still guiding light. So these fibers are created using a melt flow process that combines two thermoplastic elastomers, resulting in a high index core and a low index cladding. When stretched, bent, or indented, they exhibit predictable and reversible changes in light transmission based on wavelength. Understanding how these deformations affect optical properties is vital for creating reliable sensors that can detect extreme mechanical forces. Let's continue with an overview and introduction to wearable functional textiles. Wearable functional textiles detect human motions, deformations. There are lots of applications for them, including health monitoring, sports, human-machine interaction. There are of course some sort of challenges, but the main challenge is that they must tolerate a wide range of deformations for accuracy. Advances in materials have enabled electronic textile sensors that use resistive, capacitive, and inductive detection methods. Combining materials with different properties is crucial for maintaining performance. This often involves complex manufacturing processes. Examples include depositing conductive nanoscale components on PDMS, injecting liquid metal into elastomeric fibers, and stacking silver-plated textiles with PDMS. A promising method for monitoring body motion uses optical fibers integrated into fabrics. These fibers consist of two transparent materials with different refractive indices. Standard materials like silica and PMMA are rigid, while elastomers and hydrogels offer better flexibility. Current production methods are limited to lab scale, restricting fiber length and speed. Recent work focuses on physically cross-linked thermoplastic elastomers, which allow for high-throughput manufacturing. However, scalable production of stretchable optical fibers are reliable sensing at strains over 100% is still needed for effective body monitoring. In this paper, the authors present a scalable method to manufacture highly stretchable optical fibers using a one-step continuous co-extrusion process producing hundreds of meters per hour. These fibers guide light through total internal reflection with a high refractive index core of 1.52 and low refractive index cladding of 1.36. They can endure extreme deformations, causing predictable reversible changes in light transmission. This allows for a fiber-based sensor to quantify mechanical stimuli, demonstrating reliable detection for actual strains of up to 300% at first for optical fibers. The authors demonstrate the potential of their optical fibers in body monitoring with three prototypes. That's what I'm talking about. A knee brace that monitors knee angle during sports or rehab. The second one was a glove that tracks finger movement for controlling a virtual hand. And the third one was a tennis racket that detects ball impacts. Okay, now let's talk about the fabrication of stretchable optical fiber. Let's start with the material selection. They mainly focus on thermoplastic elastomers because they can be easily melted and stretched. They evaluated several options based on two key properties. The first one was refractive index contrast, which was vital for guiding light effectively, and the second one was transparency, because they want to minimize light loss. From their evaluation, they choose Starclear 1044 as the core material with a refractive index of 1.52 and an elongation at break of 693. The second one was the cladding, which Daikin T530 was chosen. with a refractive index of 1.36 and 580 elongation. These materials provide a significant difference in refractive index while also having similar mechanical properties, which is important to avoid failure. Now let's talk about the fabrication process. They used a co-extrusion method, which as you can see in figure 1b, this setup involves two extruders that feed the melted polymer into a custom nozzle to create the core and cladding structure. They can also control the diameter of the fibers, which they standardize at 1 mm, and they achieve an impressive output of 200 mm in just 1 hour, as it shows in figure 1c. Then what about optical performance? The fibers guide light effectively. They demonstrate this by turning one into a knot, which is denoted in figure 1d. An optical microscope image available in 1e showed that red light is mostly emitted from the core, confirming successful light guiding. When stretched, the fibers change the color of the emitted light from white to red, as denoted in figure f, indicating how light attenuation varies with strain. Now let's discuss the mechanical and optical properties of the stretchable optical fibers. To evaluate these properties, they performed tensile testing and a spectroscopic analysis. The core cladding fibers maintained integrity up to about 545% strain, denotes in figure 1, this one. The standard spandex, if you compare that amount with, you can see that spandex have 100% modulus of 0.76 MPa and a failure stress of 10.66 MPa, which shows that why they choose that. They also tested the fibers under cyclic loading. A fiber was stretched between 0% and 300% strain for up to 100 cycles. Initial plastic deformation was 17%, increasing to 34 after 100 cycles. To improve performance, they presented the fiber to 40%, resulting in entirely elastic behavior, denotes in figure B. For optical performance, they used cutback method to measure propagation losses. As shown in figure C and D, light intensity increased exponentially with decreasing fiber length. The attenuation coefficient varied with wavelength, being higher at shorter wavelength compared to longer ones. Defects in the fiber likely caused these losses, leading to light scattering, as you can see in figure D and F in this slide. They compared core cladding fibers to core-only fibers in air, water, and silicone oil, denotes in figure F. The core-only fibers showed significant transmission loss in higher refractive index media, while the core cladding fibers maintained consistent performance. About the deformation sensing. To measure this, the fibers were stretched repeatedly from 48% to 300% strain, while monitoring light at 645 nanometer, 750 nanometer, and 855 nanometer, as shown in figure A. They found that transmission decreased with elongation, and this effect was reversible and consistent over at least 100 cycles. Shorter wavelengths showed greater losses, aligning with earlier measurements. They also tested the fibers under bending and indentation, as it's visible in these two graphs. Bending involved creating a minimal radius where sections touched, while indentation involved pressing down to 0.625 nanometer deep. Both actions caused transmission losses related to the degree of deformation. However, unlike stretching, these losses weren't much affected by wavelength, indicating light struggled to meet the critical angle for total internal reflection. Regarding mechanical response, transmission loss changed slightly in the first few cycles, but stabilized after cycle 10, showing good reversibility. Maximum deviation due to hysteresis were minimal 5% strain, 0.6 nanometer bending radius, and 0.1 nanometer indentation depth. And fluctuations during relaxation were much smaller than this hysteresis. Regarding human activity monitoring, they developed a knee brace that continuously monitors knee angles in real time. This is the one in the left corner of this picture, which is figure 4A. This device uses a fiber fixed on the knee, which stretches as the knee bends. Light from an LED travels through the fiber to a photodiode, producing a signal proportional to the transmitted light intensity. They verified its performance by comparing sensor output with actual knee angles measured visually in Figure B. The results showed a linear relationship, allowing precise tracking without complex data processing. They also tested the knee brace while a subject walked and ran on a treadmill. The real-time data closely matched video analysis of the knee angle, which denotes in Figure C, demonstrating its potential for rehabilitation and athletic assessment. The second prototype was a glove equipped with fiber sensors for each finger, as is visible in Figure D. This glove captures finger movements and translates them into a virtual hand model in real time. Users interact with virtual environments or control smart devices, even playing a virtual piano by moving their fingers. And they created a tennis racket as well that detects where a ball impacts, which is available in Figure F. A mesh of fibers on the strings connected to LEDs and photodiodes. When a ball hits, it indents the fibers, causing a dip in transmitted light intensity, which denotes in Figure G. This setup allows precise localization of impact, enhancing training and analysis in sports. So to wrap it up, they have successfully demonstrated the scalable fabrication of highly stretchable optical fibers made from low-cost thermoplastic elastomers using a one-step co-extrusion process. These fibers guide light with an attenuation coefficient of 0.8 dB and can withstand extreme deformations with an elongation at break of 545%. The fibers exhibit predictable and repeatable transmission losses when subjected to stretching, bending, and indentation, even after 100 cycles at a strain of 300%. This level of performance is unmatched by any other reported stretchable optical fiber systems. To showcase their utility, they also created 3 integrated wireless sensing systems. The one was a knee brace for monitoring knee movement during activities, the second one was a glove for real-time finger tracking, and an impact sensor in a tennis racket. These applications highlights the fiber's excellent performance under large strain and high-speed impacts, making them suitable for real-time human motion monitoring with great precision. Overall, these fibers provide a really versatile platform for advanced sensing devices in health monitoring, rehabilitation, physical training, human-machine interaction, functional exercise, and even IoT devices control. Thank you so much for listening to this presentation. I would be happy to receive any comment you may have. Thank you.